My name is V40 Fowler. Normally when I introduce myself, people always ask, is your real name Kevy? And is it short for Kevin? So proactively, Kevy is my real name, and it's not short for Kevin. So we'll get that out of the way so we can focus on SQL Server database forensics. There's some familiar faces. Earlier today, this morning, David Litchfield spoke on database forensics, focusing on Oracle. This talk is going to focus on SQL Server database forensics. You might find some techniques that are somewhat similar, though, but there's absolutely a new twist, and there's a few other things that we're going to cover today. The way I've laid out the presentation is at the early part, what we're going to do is we're going to go over a forensics primer, and that's going to cover some key concepts that will help us out later in the presentation when we get down to the nitty-gritty and to the hexadecimal, etc. So the first slide, why are databases critical assets? Databases hold critical information. That point is pretty self-explanatory. Industry trends are scaling in versus out, meaning what people are doing are they're taking numerous database servers and they're consolidating them on fewer database boxes. And in most cases, they're doing this to save cost or for ease of manageability. But what this is doing is it's creating these honeypots, or gold pots, I should say, of information that attackers frequently try and target. Data security legislations and regulations out there. California led the way with SB 1386 a few years back, and I believe now there are 34 or 35 other states that actually have regulations in place that force companies to report data security breaches. Due to this, the database security breaches are front page news. People take them extremely seriously. Some of the larger data security breaches that have come to light recently have been TJ Maxx, which there was 45.7 million credit and debit card numbers disclosed, and of course Card System Solutions that had 200,000 credit and debit cards disclosed. Database forensics is a fairly new concept and term. Whether you Google it, whether you do your own independent research, there's not a lot of information out there in the industry. So when most people do investigations, they take a look at a system that an authorized user has gained access to. In most cases, they assume worst case scenario that anyone on the system did have access to the database and did have access to that critical information. So with the concepts we're going to cover today, I'm going to show you some ways and some different techniques that can help justify exactly what happened on the database server. Traditional investigations often exclude databases. That goes without saying. So based on my illustration here, I have an intruder with wreaking havoc on a database server. And what normally happens is there's evidence that's on the database system. A lot of this evidence is in memory. That memory sometimes is paged out to a file system. Some of the evidence as well is written directly to the file system, and that would be in the form of a system event log or a SQL Server error log. So with typical forensic investigations, in a lot of cases you're going to do your dirty word list searches on memory, on the file system, or review the system event logs and the SQL Server error logs. But there's very little focus today on the actual database files, which are highlighted in red. So that means the actual data files and the transaction logs within the actual database server. These files contain a ton of evidence, and we're going to look at that in more detail today. So this solution, database forensics, in terms of definition, it's the application of computer investigation and analysis techniques, and that's put together to gather database evidence suitable for presentation in a court of law. Some of you might see this as being familiar, but it's pretty much the definition of computer forensics with a database twist to it. Some of the benefits you can actually get from conducting database forensic investigations, or you can retrace user DML and DDL operations. By DML operations, that stands for data manipulation language. So any inserts, any updates, or any deletes, you can actually retrace that through database forensics. In addition to DDL operations, which are data definition language, and that involves changes to the actual schema of the database. So that would be if someone creates a new user account, creates a table, someone adds additional privileges to a user. All of these actions will be tracked under DDL operations, and you can retrace both with database forensics. Another benefit is you can identify data pre and post-transaction. So it's one thing to know, hey, some unauthorized user updated all employees' salaries to $100,000 per year. It's another thing to know what the value is before the update. So database forensics will actually tell you what the data was prior and after the actual transaction took place. Something else you can do with database forensics is you can recover previously deleted data rows. So again, knowing a deletion took place is one thing. Knowing what information was deleted is something else, and all of this is what we're going to cover later in the presentation. So with databases, they definitely can help prove or disprove a data security breach. So yes, an attacker had access to the database. Did he have access to the objects that contain sensitive information? If he did, what did he actually do within the database? Did he read data? Did he modify data? Did he delete data? All of these are ways you can determine what happened during a database forensic investigation. The best points with the concepts and the techniques that we're going to cover today are they're designed for the real world, meaning you don't need third-party login applications installed and configured. You don't need previously created DML or DDL triggers that are already in place. All the techniques we're going to cover today don't require any dependency on any of these items. So in most cases, when you do forensic investigations, you're going to come across a database server that's ill-equipped for a forensic investigation, and a lot of these techniques will definitely come in beneficial to you. So starting the forensic primer, database files. The data files hold the actual data within the database. By default, when within a SQL Server database, the name of a data file will be the name.mdf. And all of these MDF files contain thousands and thousands of actual data pages. These data pages have page headers, they have data rows, and they have a row offset array. The row offset array just denotes the beginning of the actual data rows. The data rows contain the actual table data that's in the various database objects. And the data rows that are in place within a SQL Server data page can be either a fixed length or a variable length. Fixed length data rows, the structure is extremely straightforward. For variable length data rows, it's a little more convoluted because there's additional overhead to mark when a column stops and where the next one begins. So today we're going to do it the hard way. We're going to focus on the variable length data rows, and we're going to cover that a little bit later in the presentation. In addition to the data files, the log files are denoted with a .ldf extension, and these hold any data required to reverse transactions. So all the DML operations and your DDL operations are logged within a transaction log, and the physical LDF, or the physical transaction log, underneath the hood contains multiple VLFs, which are virtual log files. A subset of the virtual log files are active at any one given point in time. So a VLF will be active. It will record transactions. When that VLF is full, it will move on to another inactive VLF. This process continues until there's no inactive VLFs that are free, and it will start to write to free space. Space is reclaimed within the transaction log by when a database backup is performed. When a database backup is performed, the active VLFs are marked inactive, and the space is reused. In addition to when a database backup is performed, when someone truncates a transaction log, the same procedure will take place. When a transaction log grows to 70% of its capacity, the same operation takes place as well. So SQL Server has these internal routines that help manage the size of the actual log files. And when truncation needs to happen, truncation happens at the VLF point, meaning the VLF is a truncation boundary. If there's a VLF with 100 transactions recorded in there, one transaction is still active, SQL Server will not inactivate that VLF. It will keep the entire VLF active. And according to Microsoft, although you might assume that reading the transaction log directly would be interesting or even useful, it's just too much information. Today, we're actually going to take a look at the transaction log, and we're going to make sense of too much information, according to Microsoft. Based on research I've done, no one has documented the innards, for lack of a technical term, of the transaction log. So I've gone ahead and done that for you today. Inside the transaction log contains over 100 data elements, meaning 100 columns. What that means is each transaction that's recorded within the transaction log can contain 100 different data elements. We have an hour and 15 minutes today, so of course we're not going to cover all 101 data elements. But what we will do, we'll focus on the data elements highlighted in red, which are operation, transaction ID, page ID, slot ID, offset and row, SPID, row log content, 0 and 1. As opposed to giving you guys the definition of all of these transaction log items now, what I'm going to do is throughout the presentation, when we come across the actual element, we'll discuss it then. That'll make it easier for you to comprehend the principles behind that. First one we'll start off with is a SPID, which is a server process ID. What a SPID is, it's used by SQL Server to track a given session within the database. So SQL Server itself uses SPIDs to track what it does internally within the database, and it does the same thing for any user connections that are external to SQL Server. Any transaction log activity is logged directly against the executing SPID, so that helps us definitely for computer forensic investigations. In addition to SPIDs, data type storage and retrieval is something that we should definitely be aware of within SQL Server. SQL Server supports 31 different data types. Various data types are stored and retrieved differently within SQL Server. Little end-in ordering is applicable to selected data types, just like on Microsoft operating systems. SQL Server uses the same end-in ordering. And storing and retrieving the value 21,976 in various data types results in the following. This is an example of how data is stored and retrieved with SQL Server. So using the character data type, the on-disk value is 32, 31, 39, 37, and 36. What this is the hex representation of the ASCII equivalent of 21,976, meaning 32 maps to the number 2, 31 maps to the number 1, and so on. So character is pretty straightforward in terms of the way it's stored and the way it's retrieved by SQL Server. Integers, the on-disk value is D855. Of course, because an integer is converted to a decimal, we would need to convert that to little end-in ordering. So D855 in reality is 55D8. That hexadecimal number converted to a decimal brings us to 21,976, and that's what SQL Server does in the background when we retrieve that value. Date time, like integer, is a hexadecimal representation of a decimal number.